The last transformation we have to look at is called a dilation, and you've probably heard this word before. If you've ever been to the eye doctor, you've gotten your eyes dilated, and that basically means the pupil gets a lot larger, making it more sensitive to light. So we're going to look at the enlargement and shrinking of different objects. Thus far, we've only been looking at isometries, meaning we've been taking different objects and translating them around, but we haven't changed the size or shape. Now we are going to. So a dilation is the only non-isometric transformation we're going to look at. And what we need for a dilation is both a center of dilation and a scale factor. You learned scale factor in terms of similar triangles before. It's a very similar concept. So you have a center point, and you have some preimage A, B, C. What we're going to do is increase that by some scale factor. In this case, we call that scale factor R, which is 1.5. We take triangle ABC and increase it by the scale factor 1.5. How we do this is in terms of distance from this center point, which is labeled O. So we take OA and we multiply it by 1.5. So OA times 1.5 gives us the new length OA prime, which is represented down here. OA prime is equal to 1.5 times OA. Similarly, we have 1.5 times the distance OB is going to give you the larger distance OB prime. And then finally, OC prime is 1.5 times the distance of OC. What does this mean to you? Well, if OA, let's say, was 10, then what we could do is find OA prime. OA prime is going to be equal 1.5 times 10, which 1.5 times 10 is equal to 15. So the distance from the center point O to A prime is now 15. Suppose OB was 8 and OC was 12. Challenge yourself to figure out what OC prime and OB prime would equal. Let's look into what happens if R is less than 1. So in this case we have R is equal to 1/4. Notice that the larger figure here is the preimage and the smaller figure is the image. So if R is 1/4, that implies that we're going to shrink down our original figure. Rectangle M prime, N prime, O prime, P prime is a dilation. It's still called a dilation even though it's shrinking down. Keep that in mind. Of the larger rectangle. So by the properties we just learned, XM, where X is now my center point, so the distance from X to M prime is going to be equal 1/4 of the distance from X to M. X to N prime is going to equal 1/4 of the distance X to N. Similarly, we can write down expressions for the last two. We have XO prime is equal to 1/4 of XO. And this can be rearranged. So we can actually write that XO is equal to 4 times XO prime. And this is helpful to us when we go to find different measures. So suppose that MN was equal to 40. How would you find M prime, N prime? Well, we know that this is a 1/4 reduction in size. So if we take 40 and divide it by 4, we take 1/4 of 40. Another way of writing that is 1/4 times 40. We get that this is equal to 10. So M prime, N prime is 10. So we can use dilations to solve for missing lengths of figures that are either shrunk or enlarged. To summarize what we just learned in the last two examples, we had the first situation where R was 1.5, so R was greater than 1. The dilation was an enlargement. In the second example, where R was 1/4, meaning it was between 0 and 1, the dilation was a reduction in size. Think about what would happen if R was equal to 1. Just in terms of the formula that we used in the last example. If R was equal to 1, you'd have one side length equal to 1 times its image, which is just the same number. So if r is equal to 1, the dilation doesn't shrink or enlarge the object, but rather this would be an isometry. It doesn't change the size or the shape. Remember that dilations do preserve proportion of the sides as well as the angle measurement, but it does not preserve the size. So we can take a triangle, ABC, we can dilate it, and these triangles are going to be similar triangles, which means the angle measures are all the same, and the proportions between the sides must be equal. So we can take side A prime B prime and divide it by AB, which should be the same scale factor or ratio as B prime C prime over BC, which should also be the same as C prime A prime divided by CA. On the last slide we talked about similar figures a bit, so let's put that into a theorem. If we have a dilation with a center C and a scale factor of r transforming A to A prime and B to B prime, so a point to its image, then we can say that these triangles are similar. So the similarity statement I will make is triangle ABC is similar to triangle A prime, B prime, and C prime, meaning the pre-image and image are similar triangles. For these two examples, we're going to find the dilation image or look for the pre-image based on the given information. Remember that we always take the original lengths and multiply by the scale factor r to find the image. So in the first example, we take AB and multiply that by the scale factor r. Side AB is 24 and r is 2, so 24 times 2 is equal to 48. 48 represents A prime, B prime, the length of A prime, B prime. Now in this second example, we're working backwards. We don't have AB, but we want to find those. What we do know is that AB times the scale factor is equal to A prime, B prime. So we'll plug in the values that we know. We don't have AB. We know the scale factor is 2/3, and that's equal to A prime, B prime, which is 32. Solving this algebraically, we need to find AB. So I'm going to multiply by the reciprocal 3/2 on both sides. By doing this, 3/2 times 2/3 is just 1. So we get 1 times AB. Therefore, AB is equal to the product 32 times 3/2. 32 times 3/2 is equal to 48. So now AB is equal to 48. I've started by drawing out the coordinates and the triangle that they asked us to draw in this example. There's a theorem printed in your notes, and what the theorem says is if you have a coordinate that is translated using a dilation centered around the origin, then the image of the original coordinate is just going to be the scale factor, r in this case, times the x and the y value. So you're going to take -2 and 1, the x and y values of A, and just multiply that by your scale factor. And in this case, the scale factor is k, which k equals 2. So to find A prime, I take and multiply -2 times 2 for the x coordinate, and 1 times 2 for the y coordinate. And this is equal to -4, 2. Similarly for B prime, I'm taking 3 and -3 and multiplying them both by k, which is the scale factor of 2. So I get 6 and -6 for B prime, and C prime is 4, 8. Lastly, I just have to represent this on the graph. Plotting A prime, B prime, and C prime, I drew out my image, and you'll notice that it is an enlargement of our original ABC, the original triangle. In a case where we're given both the pre-image and the image. So we have the pre-image, the larger square, A, B, C, D, and the image of that, A prime, B prime, C prime, D prime, being the smaller square. And we want to find the scale factor. First thing you want to make sure is, well, this figure is shrinking down. So we know that R is going to be between 0 and 1. And to find the scale factor, what we have to do is just take the quotient of the image length divided by the pre-image length. So we can look at the length from the origin, x, to the image, which is 2 units, and divide that by the pre-image length, which is 1, 2, 3, 4, 5 units. We have that the scale factor in this case then, SF I'm going to call it, is equal to 2/5. The most common error that is done is that this fraction will be written flopped upside down, so it will be written as 5/2, which is why it's important to ask yourself ahead of time, should my scale factor be larger than 1, meaning it's getting bigger, the figure's growing, or should it be between 0 and 1? And that's the catch. So my answer in this case, 2/5, did turn out between 0 and 1. 2/5 equals 0.4. In this last example, we're asked to find the scale factor of the dilation, and we're dilating figure A to figure B. So in this case, figure A is the pre-image, and figure B is the image. So what we have to ask ourselves is, look at the sides and the corresponding sides, and we're kind of looking at similar figures in this case. So to go from 8 to 4, we're going to cut that in half. So this is a reduction by 2. Scale factor in this case is 1/2. Now to find all of the missing sides, we can take sides in figure B and multiply by 2. Or we can take sides that are given in figure A and divide by 2. Since all of the sides in this case are given in figure B, I'm going to multiply these by 2 to get to the values of A. In this case, since y corresponds to 3, side length 3, we have y is equal to twice 3, which is 6. X is then equal to twice of 2, which is 4, and finally z is equal to double of 7, which is 14. Make sure to review your notes and go back and check to make sure that you've answered all the additional questions that go along with the video to be prepared and ready to come to class.